Okay, so before the break, before Thanksgiving, we were looking at correlation and seeing how well different items were matched up. So I can't even remember. It's been so been a while. I can't even remember an example. Let's see. For instance, we said that the weight of a person and the calories consumed, we would expect to have a positive correlation. Meaning, if they ate a bunch of calories, they'd probably have a larger weight. Now we're actually going to take those scatter plots that we created in section 1, 5.1, and put a line to them. Come up with an equation for it. Good thing is that the calculator is going to do pretty much all the calculations. Today won't be calculation heavy. It'll just be a lot of button punching on the calculator. So, to kind of set the stage, let's have an example. So what's our objective here? Let's suppose we have two variables. X will be the amount we spend on advertising. Y is going to be the amount of sales for that product during a given period. What's a question that I might want to answer using this data? Just kind of in general, what's a question I might want to answer if I'm keeping track of how much I spend on advertising and how much I sell? Well, do you want to spend a lot on advertising and have sales decrease? No. You want to perhaps see if your increase in advertising leads to an increase in sales. So the objective of a regression analysis is to use information about one variable, X, to draw conclusions about another variable, Y. So our X variable is the independent or explanatory variable. The Y variable is our dependent or response variable. And we're going to use values of X to predict values of Y. I'm going to emphasize predict here. We're not saying that these will be the exact values of Y. They're not the exact, more than likely. Our points are the exact values. This regression line is all about prediction. So scatter plots frequently will exhibit a linear pattern. So when this is the case, it makes sense to try to find a line that describes that relationship. And that's close to as many points as possible. So this line is called the line of best fit, or as we're going to call it today, the least squares regression line. So that formula will be y hat equals a plus bx. In case you don't know where we're at the top of page 7 now. Y hat is the predicted y. That's what we think may happen. And make sure when you are working these problems that you put the hat on the y. I don't know why that text is so small. But anyways, make sure you put the hat on the y here. If you don't have the hat, you're saying that is the y. So with the hat, you're telling me that that's a prediction. B is our slope. It's the one by the x. I know usually we see it like y equals mx plus b. I know that's usually the format that we see it, but we're not using that format. So B is the slope. And of course, since it's the slope, that means it approximates the amount by which y increases if x increases by 1. A is our what? What do y'all think A is? B is the slope. What does that make A? The Y-intercept. That's right. A is the Y-intercept. It's the approximate height of the line when x equals 0. Now, in yesterday's activity that some of y'all were like, ah, gosh, this is like so algebra 1. I'm so over this. Did we really have to go back and do this? We said that there are some cases where it wouldn't make sense for the line to keep going. So in that case, there are some instances where the y-intercept has absolutely no meaning whatsoever. For instance, yesterday, we can't buy negative land or negative gas. It just doesn't exactly work. And even if, let's say we were buying 0 acres of land, if the intercept is negative 500, do you think someone's going to pay you $500 to come look at their land? More likely, no. More likely, no. They won't. Unless they're just really desperate and they're really trying to sell it, they're probably not going to pay people to come look at the land. So that's great and all, but how do we get the slope? Well, we have this lovely formula here. Our slope is equal to the sum of x minus x bar times y minus y bar. Divided by the deviations from x bar squared. Looks like a lovely formula, doesn't it? So it looks like one y'all want to have to compute? No? Okay, well, let's see if the next formula looks like something I want to compute then. The Y-intercept. A is equal to the average of the Y's minus B times the average of the X's.
What is the LSRO again?
Least squares regression line.
Okay.
So what do y'all think about A? Does that look like something I may want to compute? That looks doable? Well, the good news is you won't have to compute either of those. The calculator will do it for us. So the least squares regression line is the line that minimizes the sum of the squares of the deviations from that line. Now, right now, you may be thinking, okay, yeah, sure. That makes a whole bunch of anything but sense. That does not make sense at all. Hopefully, by the end of this next example, it will make a little bit more sense. But before we get into this example, if you don't have your calculator, is there anyone that would like to borrow mine? Yeah. Just so y'all know how to do the steps.
Thank you.
You're welcome. Okay, so for this first example, we're just going to ignore this formula. You can write it down if you'd like, but we're not going to use it to calculate B. So this is another formula to get B. Yeah. Looks even more fun than the first, doesn't it? Yes.
I'll check it real quick.
Yeah. Okay, so let's suppose we have this data here, and they already did the scatter plot for us. We just have 3 points: 0, 0, 3, 10, and 6, 2. So let's try to fit a line by drawing through what appears to be the middle. We're not going to be too precise right now. We're just going to be like, oh yeah, that looks like the middle. Let's go. See what happens. So we're going to say this looks like the middle. I mean, it kind of does, maybe. So let's draw this line on that first scatter plot that y'all have at the bottom of page 7. Y hat equals 4 plus 0.5x. Okay, once we get the line drawn, let's find the vertical distance from each point to the line itself. Actually, I said that backwards. From the line to the points. So for instance, how far did we have to go to get from the line straight down here to 0, 0? How far would this distance be here? Would it be 4 if I'm going down? The -4, because I'm going down from the line down to the point. So -4 would be that distance. Okay, what would it be the next one? He actually just went down there to check in. So what's the distance from this point, or from the line up to this point? What's that distance?
Oh,
Well, first I have to know what this point is. I know it's going to be 3, but if I plug a 3 in here, what's it give me for my y value? Yep, 5.5. Okay, so I've got to go from 5.5 up to 10. How far is that? What was that, Olivia? 4.5. That's right. So 4.5. And then I do my next point. I go from the line, which I got to figure out what point this is on my line even. So let's plug a 6 in for x. And what would you get for this point? 6 and what? 7, that's right. So now, how far do I go from the line down to the point? Would be +5?
we're going back.
-5. Okay, so we found that. Now let's find the sum of the squares of these deviations. So what we need to do is add up -4 squared plus 4.5 squared plus -5 squared. If I add those up, what would that get me? So what do you get if you add those together? And it will be a decimal, so if you're like, I got a decimal, don't know if it's right.
I agree, the number in front of the decimal, right?
Yeah,
Is it 61.25?
it is. No. 61.25. Okay, so with that line, our sum of squares is 61.25. But we don't know if that's the minimum sum of squares. Because a least squares regression line tries to find the least of these values here. So it would sit there. This is kind of what the calculator, well, it's not what the calculator is doing, but it is. Essentially, the calculator is sitting there and trying to graph a ton of lines and then seeing, okay, which one of these gives the least squares? Now, like I said, that's actually not what it's really doing. I don't know if y'all remember matrices in Algebra 2. Right, where you have something that looks like this, and there's a bunch of numbers in here.
I remember.
Remember that?
Yeah, I didn't like that.
Yeah. So what's actually going on is there's a matrix that when you put the data in, the calculator turns it into that matrix, does the matrix algebra, and boom, gets the answer. But I'm not going to even go into any of that. Because quite frankly, I didn't really care for it when I learned it. But anyways, that's what we're going to do next. We're going to see if we can minimize that. So on to the next page. We want to use a calculator to find the equation for the line of best fit. So you may be wondering, okay, well, how are we going to do that? That's great, but how do we do it? Well, let's take our points. If we think of them, if we write our points down, 0, 0, 3, 10, 6, and 2, put the x's in L1, the y's in L2. So my new calculator program looks a little different, but let's go with it. Okay, so let's see. I need to go Stat, Edit, and then let's put our 3 points in. 0, 3, 6. 0, 10, and 2. Okay, who remembers before break how we ran a regression? Stat, calculate, yep. So before break, we did option 4, yes. But that's because I didn't realize all of the notes are actually in the format of option 8. It'll give you the same line. It's just, notice the formats are just slightly different. So we're going to do option 8. That way it gives us the format of what's in the notes. So hopefully you put your X's in L1 and your Y's in L2, so then you don't have to worry about changing those. Now, one new thing I want to show y'all is how to store the regression equation. That way, when you pull up the scatter plot, it will have the equation saved in y equals and will automatically draw the line for you. So where it says store regression equation, if you get this screen, if you don't, you just put another comma and then still pick the Y1 or pick Y1 like we're about to.
Stack count 8 and then
You put L1, comma L2. And put another comma. And then now we want to go to, we want to hit the vars button, the variables button. And it should come up and give you this option of doing vars, Y vars. Yours probably doesn't say color up here. But we want to go over to Y vars, select function, and then Y1. And what that'll do is when we run this regression, that'll store the equation into Y1. So that way it'll graph the line automatically when we do a scatter plot.
so I don't think I did it right. I went back, and now I'm back to Mars. I don't know, like it just said like, when I started talking, went back to Mars. What do I do now?
Let's see.
I'm back at this point. I'm there for this.
Let's see what we did with Y1. Function. Now Y1. And then hit that. And the work block doesn't happen. But once we get our numbers down for here, I'm gonna go press Y equals just to kind of show you, hey, if it's so good.
All right.
Yes.
And this is how we do the 9.1 to it and minus like the Y1 thing. All right, thank you.
How far are we? We're not very far.
Page 8.
We're top of page 8. Yes.
Yeah.
Yeah. Okay, so mine just gives me A and B. That means I haven't done what? Since I don't get R and R squared. What have I not done?
You haven't got the Mars yet.
I haven't gotten the R's, but why isn't it showing the R's? What did I not do? Diagnostic. There you go. So how do we turn diagnostic on?
I thought it was still on.
Second zero,
Yep.
goes down forward, diagnostic on.
Yep. Okay, there's diagnostic on. So now let me rerun my regression.
I remember looking what I think.
Okay, now I have my R's. For this problem, I don't really need the R's, but just as a reminder, because we will eventually. Okay, so how can I write my so y hat equals 3 plus 1/3 x. So now let's run through this same process. Let's figure out what our deviations are from that line. It looks like we still have some big ones, especially that separation of that 3 up above. Okay, so what's our deviation? What's the vertical deviation from the line for our first point, 0, 0? What would this deviation be? Our intercept is up here at 3. So this deviation would be -3. Okay, now I need to figure out what point I'm going to be at right here on the line. What's my coordinate here? It's 3, and then I plug a 3 in for x. What would I get for y hat? 4, that's right. So what would that deviation be then? How far would I have to go from the line to my point? Want to get from 4 to 10, I would have to go up 6. And then I need to look at my other point, my last point, and see if I plug a 6 in for x, where would I be on the line? So let's see, 630. It's 2. 3 plus 2. It's like I'd be at 6, 5. If I get the vertical deviation here, I go from 5 down to 2. That would be a -3. Now, let's not square them. Let's just add them up as they are. -3 plus 6 plus -3. What would that get you? 0. Huh. You add the deviations up and that gets 0. I feel like I've heard that before somewhere, or I've said that before. Y'all remember when we did, I think it was in chapter 4. Come on, where's my pen at? When we did something like x minus x bar, and then we added them all up, we got 0. So if you add up the deviations of the least squares regression line, you'll always get 0. That's why we've got to square them. You can't just add up the straight deviations. You've got to square them. So let's do that. -3 squared plus 6 squared plus -3 squared. If I add those up, what would I get? And don't forget your parentheses. $54. So how does this value compare to the one that we calculated on the bottom of the previous page? Is it higher or lower? It's lower. Yep. That's right. So on a least squares regression line, this is the number we're trying to minimize. That's what we want to minimize.
This is what we're doing when they ask for a line of best fit.
Yes.
This isn't going to be most of the final, is it? I feel like it's going to be most of the final.
No, it won't be.
I won't be, it'll be a part.
It'll be part of it, yeah. I mean, I think, if I'm not mistaken, it may be the biggest part of the final, but what I mean by biggest is like everything else may be 4 or 5%, this may be 10%. I mean, I haven't actually looked at them percentage-wise. Yeah.
Is it big?
It's 40 questions on multiple choice.
You called it that. I got it. Is it gonna be like that one test that you gave us, the little thing that the state requires to do?
No.
Okay. This is really kind of hard.
No. It won't. That one.
That was like critical thinking and stuff.
Yeah.
We don't have to do any of that.
I mean, you don't have to know how to work the problems.
Yeah, but we're gonna have to do like the critical thinking type stuff.
You won't have to do like which one best solves it. It'll be like no, you solve it.
It'll be it's either right or wrong, pretty much.
Yeah.
All right, thank you.
It'll be you solving it, and then just like a normal multiple choice test. And it'll be Scantron, so you could write whatever you want to write on your test. All that's getting graded though is a Scantron. Okay. Let's look at an example. I'm not going to read the whole example. You can skim it right quick if you want to. But the gist is we're taking mice, injecting them with cancer, and then treating them. So that's going to be an experiment. They want us to create a scatter plot for the data. X is the number of days after we inject them with cancer cells. Y is the average tumor volume. So let's create a scatter plot for this data. So which list should the X's go in, ideally? X is going L1, Y is going L2.
Can that be switched over or no?
Yeah, it can be switched as long as you remember to switch it when you run the regression. I mean, you could do it in list 7 and 10, as long as you remembered to put those for X and Y. Let me put those in the calculator while y'all are doing that, and then we'll run some regressions. Let's see. Okay. So let's have the calculator do the scatter plot for us. So to do that, we need to go to second and stat plot, which is that first button, very top row. So second, and then the button right above it. I want to make sure that plot 1 says it's turned on. If it says off, I need to click it and turn it on. Then we go to zoom, and we'll go to zoom stat, which is option 9. And then boom, it drew the scatter plot for us. So I want you to sketch that scatter plot on your paper. And try to label your points as much as possible. Or at least label your axes based on your points. So sketch that in the space where it says sketch a scatter plot. Anyone still trying to sketch their scatter plot? Still see some writing, so I'll hold up for a second. Okay, so let's now run the regression on it. These points are nice and all, but let's put a line through them to see if we can find an actual pattern. So stat, count, and then which option on the screen? 8. And now we'll actually see why we want to store the regression equation into Y1. So again, once you get to the store regression equation, or if you don't get this nice screen, just put a comma after you pick your list. And we'll hit variables, vars. We want a Y. So go over to Y vars, function, and Y1. And calculate. Boom. There's our equation. So let's write that down beside our scatter plot, and let's also make note of our correlation. Now, here's where it's kind of nice to have it stored. If you go to y equals, oh, it gets already in there for us.
Oh, that's what that thing was doing
Yep, that's what that was doing for us. It's already programmed in. So when we go to graph,
there. I did it backwards. I did the regression first, and then I went to the scatter plot and made that line.
Yep. Yep.
What's the draw line?
Yes, I would like y'all to draw the line on the scatter plot that y'all drew. You don't have to draw on the graph, just on that scatter plot, draw your regression line. And then maybe out beside it, write the equation and the correlation.
That's the negative 269.75.
That's the equation, yeah. That's your equation. At this point, I'm going to go back to the PowerPoint so we can. Okay, so we found this to be our equation. When you write it, make sure, again, you put the hat on it because we are predicting things. We're predicting the future.
And the correlation, that's just R.
That's just R, that's right.
So it's not asking you to do like a strong positive or anything like that?
We're about to.
Oh,
Because right below that, where we did our graph and everything, it says interpret the slope and the correlation coefficients in the context of the problem. So first, let's do slope. This is where yesterday's exercise that y'all probably were bored to death with, that's where it comes in. when we interpret the slope. So remember yesterday our formula that or template, it's not really a formula. The template, we said to do slope, I'm going to write it up here. V, and then we said that the y variable. What's our y variable? Average tumor volume. So the average tumor volume again, this is for our slope. The average tumor volume. What did it do based on our slope here? Did it increase or decrease?
Increase.
It increased. How much?
37.25.
37.25 millimeters cubed for each. That's part of our template. For each. And then we have our x variable. We could say something like day for each day after injection. The average tumor volume increased 37.25 millimeters cubed for each day after injection.
Mr. Phillips,
Yes,
we're not supposed to do it, it's just the final.
that's right. Just the final. Unless y'all want to test over this.
Good.
You good?
All right.
I'm gonna say we could do it Monday and then do the final Tuesday.
My grade is far away from this spot.
Okay, so that's our interpretation of the slope. Now let's have the interpretation of the correlation coefficient. So we haven't done one of these since before Thanksgiving. Now I'll say that like we've been back for a while. We've only been back 2 days. But still, that one's going to be down here. It's going to say, well, core. So there is a what? If you're kind of stuck, maybe you want to look at the top of page 6. Strong positive, good. There is a strong positive. Any kind of correlation?
Linear.
Linear correlation. Between average, I'm going to really abbreviate this because I'm like out of brain. Average volume and days passed since injection. So now we've interpreted the slope and the correlation coefficient. Let's flip over to the next page. I'm not going to go to the next slide yet. wants to talk about the Y-intercept, which that's the next question on the top of page 9. Does the Y-intercept have any meaning? So which one of these numbers up here is our Y-intercept?
Negative 269.
Negative 269. Does this number have any meaning?
Yes.
Okay, what's the meaning in the context of this problem? So if we think back to what we said yesterday, we would say initially the tumor size was negative 269.75 millimeters cubed. That's what I'm asking you. How does that make sense? Does that number have any meaning then?
No.
No. Nope, it does not. So Y-intercept has no meaning. And then we could say tumor size can't be negative. So the Y-intercept has no meaning because tumor size cannot be negative. Okay, I think we've kind of done all the damage we can do with this slide. So now they ask us to predict the average volume of the tumor for 20 days after the injection. What would this 20 go in for? The X or the Y? X, that's right. So let's copy our equation down. Y hat equals 269.75 plus 37.25x. And then we're going to plug the 20 in for the x. Y hat equals negative 269.75 plus 37.25 times 20. And if we type this in our calculator, what would we get for the tumor size? What do I get for tumor size when you type in the equation with the 20? You should have gotten 475.25 25 millimeters cubed. So that's our predicted size. Now let's do the same thing except do 5 days. So now let's do 5 days. Which is the next one, next line of text on your page. What would that give you with 5 days? Should be a negative number. Negative 83.5 millimeters cubed. Does this make sense? Why not? We got a negative tumor size. Now, let's just make that negative tumor size.
What if the answer was negative what?
Negative 83.5. Let's take a look here at our original data though. When we plug in the 20, it's kind of sitting right here between the 19 and the 23, right? For the x's. When I plug in a 5, the 5 is way over here. This shows the danger of extrapolation. Extrapolation means that you are using a data point that's not in your range. Our equation here is only good between 11 and 27, or somewhere pretty darn close to it. If you're way out, whether you're below or you're above, we don't know if the model holds true. I mean, we should not extrapolate. No. I mean, yes, our line. Oh, let me see, go away. Our line may look like this between 11 and 27, but then something like this could start happening above. I mean, I'm exaggerating, but hopefully you get the point. You could have something like that happen above and below. All we know is that between 11 and 27, we're good. You get outside that, it doesn't mean anything. As we saw by this 5 days, we have a negative tumor size.
So what would the answer be in that situation? Just put like, there's no answer?
You would just say not meaningful.
Okay. So I wouldn't put a number and say not meaningful.
Yep. There's actually a couple on y'all's assignment that's actually the answer. It's not meaningful.
Is that going to be like a multiple choice part that you can say or what?
Well, on y'all's paper, it's multiple choice. On Blackboard, it's one of those where it's like, if it's not meaningful, put NA or something like that. Yeah. Okay. We're almost done with this example. We're just doing a little bit more with it. So it says to find the mean x values and mean y values. Well, when I flipped over to this slide, it kind of gave it to you. The mean of your x's would be 19. The mean of your y's is 438.
How do you get that?
How do you get that? This is just x bar. It's just the average of your x's.
I'm looking at the bottom.
Add them up and divide by 5. Yep.
And then they do it on, 9.1, 2. That would have the equation on the bottom.
If it's asking for x bar and y bar, yes,
But if you do linear regression, then you don't have to worry about time.
correct. So now what I want us to do is go back to our scatter plot that we drew and plot the point 19 and then 19 for the x, 438 for the y. Go back to your scatter plot and plot that point.
And you start everything at the point.
No, you don't even have to do it on the calculator, just on the one that you drew on page 8, just add that point to it.
Okay.
And you should notice something when you add that point. Since we're kind of in a time crunch right now. When you add it, you should notice that it falls exactly on your regression line. You may not be able to see it, but there's a little red crosshair that I just circled. That's where that point is. It's on the regression line. It's also right next to one of our current points, but it's on the line. So will this point always be on the regression line? What do y'all think?
Yeah.
Yes, it will be.
Because of the X. I'll put it wrong.
Well, because if we look back at the equation we wrote for B to get our Y-intercept, notice we use X bar and Y bar. Sorry, to get A, the intercept. We use X bar and Y bar to get it. So, yes, it will always be on there. Just to recall, A, we said was Y bar minus B times X bar. Yep, it'll be on there. Okay, let's investigate real quick. We have like 15 minutes to investigate this. Let's investigate how the least squares regression and correlation coefficient change when different points are added to the data set. So let's suppose we have this data set. As quick as y'all possibly can, I'm not going to do it because I'm slow. As quick as y'all can, I want y'all to enter those into L1 and L2 and get us a regression line and correlation. And once you get the line, don't be afraid to say it.
What are you looking for again?
The regression line And the
That's what R is, right?
R is your correlation. The regression is where you have to plug in A and B. What did you get for the R though? 9.916. Okay, what about your regression line?
Negative 3.8 plus 1.5.
That's right.
And that's what Y hat is, right?
That's right. And then if you were to draw a scatter plot, which it asks you to, you just kind of sketch one real quick. It's not a fun scatter plot.
It's not straight.
It's not straight. Nope. Usually they're not. Mm-hmm. Okay, so now let's see what happens. And here's what I kind of want to do. Do I have a volunteer that wants to add the 0.58 to their data set? I'm going to need 3 volunteers, just so that way we can kind of get through these a little bit quicker. So someone want to add the 0.58? Just as another extra point? Yep. You want to do 5.8? Okay, so keep your same data, but then below it, just add an extra point that says X is 5, Y is 8. Yes, regression and correlation. Okay, so you're going to do 5.8. Would someone like to do 12.12? I guess did you get 5.8? Yeah, okay, let's talk about that one first. Okay, so we added 5.8 here, and we said our new R was 0.667, okay?
And how did they add it to the stat edit or what?
Yeah, just went to stat edit, and then he just added it at the end of the data, 5 and 8. And then what was your new equation?
Negative 1.15 plus 1.17.
That's right. That's right. Okay, so that's our new, when we added the 0.58, I want y'all, even if you're writing it down, I want you to pause for a second and watch our graph that's up on the slide. Watch what happens when we add 5.8. So we added it to the table. Here's our current scatter plot and regression line. And then now we're going to add 5/8 to it. What happened to the line? Yeah, this bottom part shifted upwards. And we can tell that because our intercept is larger, but our slope decreased. So this point impacted our regression results. You don't have to draw a new scatter plot unless you want to. Just make sure you write those down. Would someone like to do the point 12, 12? You already got it? Have you already done it? Oh, you can do it. Shatara.
Oh, R.959.
Okay, so R.959.
Negative 2.24 plus 1.22.
Okay, so that's right. Let's watch our graph and see it actually happen in action. So there's our original. And we can see it kind of pulls down our line a little bit. But our correlation's better. So it wasn't a terrible change, but it still pulled that right side of the line downwards. Okay, someone other than Justine. Let's do 12-0. Let us know what you get for the correlation and the regression line.
You want to round
Yeah, let's round the 2 decimal places for the regression line. 3 for the correlation.
Just look at the different rounds.
Yes, it is negative. That's our new. That's our new correlation. And then, what's our new regression line? Yeah. Let's say minus 275. Instead of plus a negative, let's just say minus 0.275x. And that's because if you think about it, we're going to be way out here and we're going to put a dot down here on the x-axis. So it's going to take this line and jerk it down towards it. And when I set this in motion, you'll see that happen if you're watching the graph. There's the original, boom. it jerks it downwards. So what this exercise shows is that the correlation coefficient and the least squares regression line are both measures that are affected by extreme values. So that's the last blank for this section, extreme values. The output is that next example, like a computerized output. We'll talk about that later. We're done for today. Yes. We'll talk about computerized output tomorrow.